Section 5 kind of picks up where Section 4 left off. The first part of this, first half or 2/3 of a page there, is pretty much more of the same kind of thing that was going on in Section 4, and then for the rest of Section 5 after that, we kind of move on to something a little different. The only thing that's different compared to what I covered in Section 4 is it's going to be more F equals MA problems, just this time the object is not moving across a level surface. Okay, you've got a box sliding down a ramp, or at least a box sliding down a ramp is what's easy to draw. I mean, this could be a skier going down the side of a mountain, but boxes are just so easy to draw. So I'm going to run through one, and then you use that to sort of inspire you to do these other ones, and that's going to be the stuff about inclined planes. So the trick is, like it says here, when you go to do your components, instead of the usual horizontal and vertical, what turns out to be easier is if you do the components along and across the direction of motion. So tip the axes so that the x-axis, instead of being horizontal, is right along the ramp, and the y-axis, instead of being vertical, is perpendicular to the ramp. And so we've got this example where I'm supposed to calculate the acceleration given these particular numbers, and this is what it looks like when I do that. Caught on something. With any F equals MA problem, everybody together, you start with the free body diagram. Don't try and write equations until you've got the picture that the equations come from. So there's the ramp. There's the box sitting on the ramp. And you have to ask yourself, what are all the forces acting on this box? Well, for any problem where you're not floating around in space, maybe I'll make that a little bigger so I've got lots of room to label things. Any problem where you're not floating around in space, you're going to have the pull of gravity, the object's weight. And it says here it's a 15 Newton box. How do you know you don't have to multiply that by 9.8? Because it's already in newtons. A newton is a unit of force. If you don't remember, look on the last page of the formula sheet. Find the line that says force. Force is measured in newtons. So you're trying to take inventory of all the forces, and if it's newtons, it's a force. So there's that. There would be friction. Friction always opposes motion. So if the box is sliding downhill, friction points uphill. And there would be the normal force, whose direction is normal to the ramp. That's why it's called the normal force. Normal means perpendicular. And that's all the forces there are. There isn't anybody pushing it or anything like that, just these three forces here. So step one, identify all the forces, draw them on the picture in the appropriate directions. Step two, components. Well, like I said, I mean, you could do the components horizontal and vertical. It's just, it would take you twice as long to solve the problem, but you'd get the right answer if you didn't make any mistakes in all of that. But it's going to be better if you say the x-axis is along the ramp and the y-axis is perpendicular to the ramp, like that. Relative to those axes, finding the components of these two forces is trivial. The normal force is right on the y-axis, so it's got itself for a y component and 0 for an x component. And friction has itself for an x component and 0 for a y component. But the weight is still vertical. Gravity always pulls directly toward the center of the Earth. So since the y-axis is tipped now, the weight will have both x and y components. Like that. So we need an angle somewhere in there to find, we have to use sines and cosines. The question says that the ramp is tilted 20 degrees, meaning 20 degrees relative to the horizontal. So if that's 20 degrees down there, this is going to be 20 degrees up in here. There's a focus. Thank you. A couple of ways of explaining that. The simplest thing to say is just that if you've tilted the x-axis 20 degrees out of being horizontal, then you will have also tilted the y-axis by 20 degrees out of being vertical. I guess I need to stand over here if I expect it to focus. The weight pulls along a vertical line. That's kind of what the word vertical means in the first place. And so you'd have a 20-degree angle between the weight and the y-axis. Or you could take more of a geometry class type of approach and say that if this is 20 degrees, then this angle up in here has to be 90 minus 20, which makes this one 20. Anyhow, hypotenuse times cosine gives the adjacent side. And hypotenuse times sine would equal the opposite side. Being the right angle here. 15 newtons is the hypotenuse. So there's what we know about the forces so far. We got them in terms of components. Now the strategy here is the question asks for acceleration. And we can get the acceleration by solving for A out of F equals ma. To be precise, sum of the forces in the x direction equals ma, because the thing is accelerating along the x-axis. Well, before you can solve for A out of that equation, you would have to know all of the forces. And right now, we don't know the friction force. Well, you can get the friction force from F equals mu n, or you could if you knew the normal force. So it sounds like the place to start is to figure out how many newtons is the normal force. Once you know the normal force, you can get the friction. Once you get the friction, then you know all the forces to put in F equals ma and solve for A. And so that's the overview. That's the strategy. To find the normal force, well, the normal force is in the y direction, so summation of the forces in the y direction is 0. the thing is accelerating right straight down the x-axis. So the y component of the acceleration is 0. And so in the y direction, you have equilibrium. You only have an imbalance of forces along the x-axis. So pulling up the y-axis, you've got the normal force. Pulling down the y-axis, you've got 14.1 newtons. Notice that you should not just automatically assume that the normal force equals the object's weight. I may have said that in last week's recording, but actually I made last week's recording about 3 weeks ago, so I don't remember what I said in last week's recording. But it bears repeating anyhow, because it's a fairly common mistake. The normal force and the weight are two distinct things. There is no reason to assume that they are equal to each other. Sometimes they are, sometimes they are not. And this is a case where they are not. The steeper the ramp, the smaller the normal force is going to be, because the normal force only has to counterbalance this component of the weight, not the full thing. The x component of the weight is what makes the thing slide downhill, and that's you know, don't mix up x's with y's. Think in terms of components. Anyhow, we know the normal force, so now I can say F equals mu k times n. Mu k, because the thing is sliding. Sliding friction is kinetic friction. Question tells me the coefficient of friction. Fourteen times 0.2 is 2.82. As far as how the units work, a friction coefficient is a dimensionless number. It has no units on it. So a number in newtons times a number that doesn't throw in any other units gives you an answer in newtons. So now, maybe I'll kind of scooch that over a little bit. Now that we know all the forces, we'll be able to get somewhere using this. So we have two forces in the x direction, and I drew it with uphill positive, which in hindsight might not have been the smartest way to set up the question, because actually the thing is going to be accelerating downhill, but well, that doesn't actually hurt anything. It's just going to make the answer come out negative. So if uphill is positive, then that would be this 2.82 for the friction force. And then pulling downhill, you have the x component of the weight, 5.13. Mass, well, here's where you could get mass and weight. Well, here's another place where you could get mass and weight mixed up with each other. 15 newtons is what it weighs. Mass would be the corresponding number of kilograms. So if weight is equal to mg, that implies, a little arrow means implies, that m equals w over g. So we've got 15 newtons for the weight. You divide that by 9.8 meters per second, and the mass of this thing is a little over 1.5 kilograms. And all that's left now is a little bit of straightforward algebra. That minus that gives you negative 2.31. Divide. And actually, the box is gaining speed as time goes by, but the reason the acceleration came out negative is just because I said uphill was positive, which, like I said a minute ago, in hindsight, maybe wouldn't have been the best possible choice, but it doesn't actually hurt anything as long as you don't get confused by the minus sign. It means it's accelerating in the negative direction. Okay, so first of all, a conceptual question where you just, it's more practice drawing the free body diagrams. Okay, so a glider on an air track, similar to what we had in the F equals MA lab. I think that one was number 4. So that should be pretty fresh in your minds at this point. Glider sliding down a frictionless incline. Well, you can read. Anyhow, pause here. And now that you've given that a fair try yourselves, I hope, let me explain the answers. So a glider on a frictionless incline. Well, maybe I should go back over here because it's just kind of a variation on what we had earlier. Here you've got a box on an incline, except friction is present. So if it's something sliding down a frictionless incline, that would be the same. Well, the question doesn't say anything about doing components. You don't have to include that. You would have this force, you would have that force, but it's frictionless, so you don't have this one. In part B, then it's a block sliding down a ramp that does have friction. So that would be exactly the situation that I had in this question here. So to draw that out, part A, box on a ramp, normal force, weight. It says it's frictionless. Those are the only 2 forces. Part B, kind of similar. You've still got the weight pointing toward the center of the earth. You've still got the normal force acting normal to the surface it sits on. This time, friction is present. Part C, a block being pulled up a ramp by a string. There's a string tied to it. So there's the ramp, there's the block. Question says there's a string pulling it uphill. So the string creates a force. There would still be the weight. There would still be the normal force. And there would still be friction, but this time friction points downhill because friction always opposes motion. If the block is going downhill, then friction points uphill. If the block is moving uphill, then friction points downhill. Well, let's see what's further down the page. Another conceptual question before we get to the one with the numbers in it. So, a car is being towed by a chain, which incidentally is not the recommended way of towing a chain, or towing a car. You should get a tow bar, and that way you don't, pulling a car on a chain or a rope, you can get in a rear end collision pretty easily. Nevertheless, every time I've ever towed a car, I've used a rope or a chain. But so it's going up a hill, and it asks to, well, again, you can read it. It's right there. So pause here. And here's the answers. Probably ought to, well, I guess I can squeeze it in underneath here. Part A. Which is larger, the pull from the chain or the friction force, or are they the same size? Well, the picture that goes along with this, both parts, you know, the picture that goes along with number 2 is the one from part C of the previous question. It's just you've got a much heavier object being pulled by a much stronger cord, but it's going to be the same 4 forces. If you're pulling the car uphill, friction's going to point downhill, and so that's the situation. So the picture that goes with 5.2 is that picture right there again. So the force out of these two that's larger is the one from the chain, the one that's labeled string in this picture. The reason is that there are 2 forces pulling downhill, okay? There is friction, and there's the x component of the weight, okay? The W sine of theta component. The cord has to pull against both of those, or I guess it's a chain. The chain has to, you know what, why don't I just change that so it says chain. Chain has to pull against not only friction, but the x component of the weight also. And let's see, it's going at a steady speed, is it? Yeah, at a steady speed, the forces have to balance. The total uphill has to equal the total downhill. Otherwise, if there was an imbalance, the car would accelerate. So chain is larger than friction. So the chain is larger. The force from the chain, I was kind of being economical with words here. The force from the chain is larger, and this is the reason why, because it has to balance against not only the friction force, but also the X component of the weight. And then the other half of it says, which is larger, the normal force or the weight? The car's weight is more. Similar to still over there at the other end of the blackboard. Maybe you remember the weight of the box. Remember, you can just look at it, it's still there. The weight of the box was 15 newtons. The normal force was only a little over 14. So, I mean, there are no specific numbers in number 2, but it's going to be the same principle. The normal force only has to balance against a component of the weight. And so therefore, the normal force is not as big. So the weight is larger. The normal force balances just a component of W cosine theta, to be precise, as you could see back over there in that other example. So finally, we come to number 3, which will probably take you a little bit of time. So pause it here. And now you can unpause. Just a moment while I make a place to write. Find the block's acceleration, which is what the thing I just got done erasing asked for, but there are a few differences between the questions. So, as always, start with the diagram. There's the ramp. We've got a box sitting on it. This time it's being dragged uphill. A 49 Newton force is pulling it up the hill. Other forces. Well, if the box is moving uphill, friction is actually acting right at the bottom of the box where it rubs against the ramp, but it's just kind of handy to draw the arrow over here where there's space for it. Friction points downhill. The normal force, as always, is normal to the surface. And the weight, which probably if I'm going to draw the weight this long, I should have made the other arrows longer, but well, I never promised that the diagram was to scale. So this says it's a 4 kilogram box. Kilograms is the mass. This is a little bit of a difference between this problem and the one that I did a few minutes ago, okay? If you took 4 kilograms and multiplied that by sine and cosine to get its components, well, aren't you ashamed of yourself? Kilograms is not a force. In fact, mass is a scalar. It doesn't even have components. So this forces would be in newtons in the SI system. Mass times gravity is equal to 4 kilograms times the gravitational acceleration, weight equals mg. 39.2 newtons is the length of that arrow. And we, just like in the other one, need to do components parallel to the ramp and perpendicular to the ramp. So like that. If this ramp is tilted 30 degrees from the horizontal, then you've got 30 degrees up in there. Hypotenuse times cosine is the adjacent side. And hypotenuse times sine is the opposite side. Well, once you've got that drawn out, it's kind of the similar sequence of events to that problem 5A that I did at the beginning. Look at the y components to figure out the normal force. Once you know the normal force, you can use it to find the friction force. Once you know the friction force, then F equals ma will give you the acceleration. Summation of the forces in the y direction equals 0. Pointing up the y-axis, you've got, I didn't actually draw the y-axis in there this time, but y means perpendicular to the ramp, x means parallel to the ramp. So up the y-axis, we've got the normal force. Down the y-axis, we've got the 33.9 Newton component of the weight. So .9 newtons for the normal force. Once you know that, equals mu n. It says both the block and the surface it's sliding across are wood. So there's that table of friction coefficients on one of the later pages of the formula sheet. You go in there and you look up wood on wood. So that comes from the table for wood on wood. And friction then is a little over 10 newtons. Sum of the forces in the x direction is equal to MA because it's in the x direction that the block is accelerating. Every place there's an arrow parallel to the surface, that's one of the terms in this summation. There are 3 of them. I have found when we're actually doing the class live, and I can go around and look at what people are doing, one of the more common mistakes is people leave out one of the forces. Probably some of you did. In the positive direction, you've got the 49. Or, well, you don't have to call that positive, but I did it the same way as the other one. As I mentioned, there's something to be said for saying that downhill is negative because that's the direction. Well, no, actually this time, kind of forgot. This time the block is accelerating uphill. The cord is pulling it uphill. So actually uphill positive makes a little more sense this time because that is the direction it's accelerating. So uphill we've got the 49. Downhill, I've got the x component of the weight and also the friction. So there, and there, they all go into that. 49 in the positive direction, 19.6 downhill for the weight, 10.2 downhill for friction. The mass is 4 kilograms. A is the thing I want to know. So you add the 3 numbers together and then you divide by 4 and that's the answer. And that's what F equals MA problems on an incline look like. Back to the note packet. Uniform circular motion, meaning something is going around in a circle at a constant speed. That's what the uniform in uniform circular motion means, is whatever it is you're talking about does not speed up or slow down. So it's like you're in a car driving around a circular track with the cruise control turned on, which is probably not something anyone would ever actually do. Racetracks are not perfectly circular, and you're not going to win the race if you just turn on the cruise control. But if you're just driving on an ordinary road and you come to a curve, it's the same thing while you're on the curve. You just don't do it for very long. Anyhow, just imagine yourself on a curve on a road. And while you're on that curve, if your cruise control is turned on, that's what we're talking about here. So, first of all, if you're going to follow that curve, there has to be a force pulling you to the side. That's furnished, in this case, by the friction between the tires and the road. Because think about what happens if that force is missing. What if there's been an ice storm? And for some reason, this part of the country, they're usually pretty good about getting right out with the sanders, and you don't really find yourself driving on glare ice. That's very rare. But if this was Alabama and they had this freak ice storm, there's probably one snowplow in the entire state, you know? So you come to this curve, and there is so little friction between the tires and the road, you might as well just say there isn't any. What happens? The road turns left, your car goes straight because your car is obeying Newton's first law. In the absence of any force, an object in motion follows a straight line at a constant speed. And that straight line leads you into the ditch on the outside edge of the curve. So if you want your car to turn left and follow the curve, there has to be a force toward the left to pull you in that direction, a force across the direction of motion, okay? A force toward the front of the car makes the car speed up. A force toward the back of the car makes the car slow down. A force directly across the road doesn't speed you up or slow you down, rather it changes your direction. To be precise, that force points toward the center of the curve, which is what the word centripetal means. We could have just said the force toward the center, but people think they sound smarter if they say things in Latin instead of English. But this is the translation into English. The force toward the center, if you say it in English, okay? Anytime you see something following a circular path, whether it's a car on a curve or whether it's the moon orbiting the Earth, okay, yeah, the moon's orbit is not perfectly circular, but it's fairly close. So as long as we're not being too precise about things, you could think of the moon orbiting the Earth as an example of uniform circular motion. You'd only be wrong by like 5 or 10%. Anyhow, if something's following a circular path, whatever it is that pulls it toward the center of the curve has to equal mv squared over r. M is the object's mass, v for velocity, r is the radius of the circle that it's following. So if the Earth had a dial on the side so you could turn its gravitational field up or down, what would happen is if you turned it up so that Earth's gravity got stronger, the moon would start to spiral in closer to the Earth. If you turned it down so that Earth's gravity got weaker, the moon would start to spiral outward. If it's going to follow a path that's a closed circle, then in the case of the moon, the centripetal force is provided by Earth's gravity. I guess I already sort of implied that. The force toward the center, if it's going to be a closed circle, has to equal mv squared over r. So a few examples, most of which I've already talked about. For a car on a curve, the centripetal force is provided by the friction. You get a friction force pointing toward the center of the curve. When we do the lab for this, lab 5, part of the lab is an object on a ramp like I was just talking about, but the other part is you just got a rubber stopper tied to the end of a string and you spin it around in a circle over your head, and you are able to determine its speed and its mass and the radius of its path to see if this formula correctly gives you the amount of force that's acting on it. Anyhow, as that cork goes around in a circle, the centripetal force is provided by the tension in the string. If the string was to suddenly break, well, it looks sort of like this. There's the circular path, like if you were looking down from above, or if you were laying on the floor and looking up at it. You see the cork going around in a circle like that. At the moment, maybe the cork is right here. There's the string. Your hand is here at the center of the circle, spinning this thing around. If the string was to suddenly break, then the string is what furnishes the centripetal force. If you all of a sudden don't have that centripetal force anymore, the cork will immediately start obeying Newton's first law, which is to say, it'll move away along a line tangent to its previous path, okay? Or at least that's what you see looking down on it from above. From the side, it would curve toward the Earth because of gravity, but, or if the moon, you know, if you had that dial I was talking about on the side of the Earth and, you know, quickly turned it all the way down to 0 so that Earth's gravitational field went away, the moon would leave us. As soon as gravity went away, it would start to follow a straight line from that point onward. And of course, a straight line would carry it away from us. So anyhow, twirling a cork around, the tension in the string provides the centripetal force. And it's not worth trying to focus that because the only part we haven't gotten to yet is here on the bottom where it says, for the moon orbiting the Earth, it's Earth's gravity. So let's just turn the page and see if the focus gets better. Top of the next page, it talks about centripetal acceleration. Newton's second law, F equals ma, says that if there is a force on something, then it'll make it accelerate at a rate that's given by F equals ma. So an object in uniform circular motion experiences a centripetal acceleration, an acceleration toward the center of the curve. Okay, if F is equal to ma, and if F is also equal to m times v squared over r, then it follows that a is equal to v squared over r. So this would seem to be a little bit of a paradox. Acceleration is, it means the rate that your velocity is changing. That's the definition. That's what the word means in the first place. So if you're driving around in a circle with the cruise control turned on, the needle stays right in front of 60 miles an hour all the time. Doesn't that mean that you're not accelerating if acceleration is the rate of change? Well, here's the thing. Velocity is a vector, okay? Its magnitude is staying the same. But see, here's a portion of the circle you're following, okay? The curve in the road. And these are supposed to be two different times. First, your car is here, and then a second or two later, your car is over here. Well, saying that it's the same speed means that the arrow here is the velocity vector. The initial velocity is an arrow that's the same length as the final velocity, 60 miles an hour, 60 miles an hour. But velocity is a vector, and it has changed direction. So acceleration is delta v over delta t, like I put all the way over here at the side. Delta v means v final minus v initial. And the way you subtract vectors is add the negative, just like with regular numbers. 4 minus 3 is the same thing as 4 plus negative 3. In the same way, v final minus v initial means v final plus the negative of v initial. The negative of a vector means to just turn it around. So if v initial points to the right and a little bit down, negative v initial points to the left and a little bit up, like this. Addition of vectors means you put them head to tail. So negative v initial placed head to tail with v final looks like that. Then you draw the resultant from the tail of the first to the head of the last. And notice delta V is not 0, okay? So you take that delta V and you divide it by the time and you have a non-zero acceleration. So in spite of the constant speed, you are accelerating due to the changing direction of the velocity vector. And notice, if you imagine these vectors drawn over here on the road, notice that that delta V would point toward the center of the curve. The direction of the acceleration is the same as the direction of delta V. Dividing by a times a scalar. Dividing by a scalar just makes the arrow get longer or shorter. It doesn't change its direction. So you have an acceleration across the direction of motion toward the center. Or if you'd rather hear a physical argument rather than all this stuff about vector diagrams and all of that, loose objects in a car can act as acceleration detectors. If you have a book sitting on the dashboard and somebody stomps on the gas pedal, what does the book do? It leaps off of the dashboard and kind of attacks you. The book appears to accelerate toward the back of the car. Well, what's really happening is the car is accelerating forward. The book, not really attached to the car, obeys Newton's first law. The book is an object at rest, remaining at rest, while the car around it is not. And so the book gets left behind. But you're judging everything relative to the car. That's your frame of reference. And relative to the car, it looks like the book accelerated toward the back, when what really happened is the car accelerated toward the front. Same sort of thing if somebody suddenly steps on the brakes. If you've got a book on the seat and somebody, a possum runs out in front of the car and the driver steps on the brakes real hard, the book leaps off the seat. Well, again, the book didn't actually leap at all. It didn't do anything. Since it's not really attached to the car, the book continues to obey Newton's first law. An object in motion remains in motion. The book keeps moving while the car around it stops. That makes it look like it's leaping off the seat. So the point is, whichever way the car accelerates, you see loose objects go the other way. So think now about what happens if you go around a curve, maybe a little faster than you really should have. If you've got, a golf ball sitting on the floor, that golf ball is going to roll across the floor toward the outside of the curve. Well, it's the same thing again. The golf ball is a non-accelerating reference point. If it's going toward the outside of the car, the outside, the side that's toward the outside of the curve, that's because the car is accelerating toward the inside of the curve. Okay, so whether you want to think of it that way or you want to think about all these arrows here, one way or another, your car is accelerating when it changes direction, or the moon is accelerating as it follows its orbit, and the direction of the acceleration is toward the center. So I'm going to do an example now. Fastest you can drive around a curve without skidding, given the materials and the radius of the curve and stuff like that. So we'll just kind of turn this around. Hi, I'm back. I'm not a disembodied voice anymore. I always figure erasing a blackboard is basically the same sort of thing as painting a wall. You got the roller in your hand and then you go like this, but you don't want to leave any lines in it, so then you take the roller and you go like, or at least that's the way I've always painted a wall, and it's the way I erase a blackboard too. Anyhow, 5B. So this dotted line here is the path of the car. And at the moment, let's say the car is right here. Excuse me. Kind of a crooked looking car. It looks a little better like that. So again, this is seen from above. Somebody's looking at your car from a helicopter or a hot air balloon or something like that. As I explained, what makes you go around the curve instead of following a straight line is the force of friction. That would be the only force in a horizontal plane. I mean, there are other forces, but the force of gravity is through the page away from you, and the normal force is sticking out of the page toward you. But as far as forces that lie in this plane, there's just only the friction force. Well, these sorts of things are really all F equals ma problems. As I've said in pretty much every F equals ma problem I've done, every place there's a horizontal arrow in the picture, that's one of the terms in this summation. Well, in this case, there's only one arrow on the picture, so there's only one force to put into the summation. And because the car is in uniform circular motion, the acceleration is equal to v squared over r. Now, one thing I should explain is that what we're dealing with here is static friction. It might seem like it ought to be kinetic friction because kinetic means when things are moving and static means when things are not moving. But, well, as the car goes down the road, every part of the car is moving except for the bottoms of the tires, okay? If you think about one particular patch of rubber on a tire, as the wheel rotates, that piece of the tire gets laid on the road and then gets lifted off again. And while it's sitting on the road, its velocity is 0, okay? Kinetic friction means sliding friction. And unless you're driving like James Bond, the tires are not sliding across the pavement. They just get sat on there and lifted off, and there's none of this kind of thing. So it's static friction. The way static friction works is it provides however many newtons or however many pounds are needed to prevent any slippage. So if you go around this curve really slowly, like 1 mile an hour, there'll be a little tiny friction force equal to mv squared over r. If you drive around the curve at 2 miles an hour, static friction will provide a larger force, 4 times as big as what you had at 1 mile an hour. If you go 3 miles an hour, static friction will provide a force 9 times, because it's v squared. The force would be 9 times as big as what you had at 1 mile an hour. So whatever is needed to provide, or to maintain, to keep the surfaces from slipping, I guess is what I should say. That's what friction provides. Well, we obviously can't go on like this forever. You can't keep saying, well, at an even higher speed, it'll provide an even higher force. There's a limit to that. There's a certain maximum force that static friction can provide, and that maximum force would correspond to the maximum speed that you can drive around this curve without skidding. because if you're skidding, that's kinetic friction. So maximum friction is equal to m times v max squared over r. Now, the maximum kinetic or maximum static friction, as we saw in, I think it was section 4, is equal to mu s times n. The normal force in this case is equal to the car's weight. As I said, doing these incline problems, the normal force is not always equal to the weight, but, well, here, if you look at the car from the side, rather than looking down on it from above, you've got the normal force up, you've got its weight pulling down. If the center of the curve is that way, that would be the friction force. But there are only these two forces in the y direction. So N has to balance mg. They'll be equal to each other in this case. So F is equal to mu N. N in turn is equal to mg. V max is what the question asked us for, the fastest you can drive around the curve without skidding. Divide both sides by m, and it's gone. M over m here, m over m there. Which is a good thing because the question didn't tell us the mass of the car, but that kind of fits in with everyday experience. You don't go driving down the road and you get to a curve and there's a yellow sign that says, well, big heavy cars can go 50 miles an hour, but tiny little lightweight cars can only go 40, and motorcycles can only go 30. It just posts it for 50 miles an hour or whatever it is. I have said that and then had people ask, well, you can drive a Corvette around the curve faster than you can drive a Hummer or something, but that's a matter of stability. A Corvette has a very low center of gravity, which makes it almost impossible to tip over. Whereas if you're driving, a box truck, then if you take a curve too fast, it's going to start to lean on you, and you don't want to be driving your box truck around the curve on 2 wheels instead of 4. So anyhow, the mass drops out. The answer will be independent of how heavy the vehicle is. Aside from that, to solve it for V, I want to multiply both sides by R, and I want to take the square root. So fill in the numbers. Radius of the curve is given in the question. 80 meters. G, okay, the next thing is mu. Mu pavement is dry concrete. You go to the table of friction coefficients in your formula sheet, and what do you know? There's an entry in that table for rubber on dry concrete, and the coefficient of static friction is 1.0. So where that came from was the handout. I looked it up on the handout, and G is 9.8. 28 meters per second. You probably want to post it for a somewhat lower speed than that because you don't want people right on the edge of losing control. You want to build in a little bit of a margin of error, but this would be where you're right on the verge of going into a skid. Okay, so a few more comments and then a whole bunch of things for you to work on. I might try and do this all in one recording instead of splitting it into two. If it's too long for you, just leave and come back, you know. That's the nice thing about recorded lectures like this. You can do it 10 minutes at a time if you think that's actually a good idea. So the next thing down the page says centrifugal force. Centrifugal with an F instead of centripetal with a P. So let's, as an example, say that you're driving along in your car, and I was talking about loose objects in the car getting thrown around by sudden accelerations. What if, just a minute, I have to trick the camera into focusing. What seems to work is if I focus it on something close and then sneak it back until it's at the same distance as the page. There we go. So let's say the loose object in your car is a carton of eggs. You've been to the store and I don't know why you don't have them in a bag, but there's this carton of eggs sitting on the back seat. Once again, we're looking down from above. You're driving a convertible and you're being watched from a hot air balloon or something like that. Anyhow, you take a curve a little too, maybe more than a little too fast, and the eggs get thrown across the car and smashed against the back door. And now you've got egg goo everywhere, and somebody asks what happened to you, and you say, oh, I took the curve too fast. The centrifugal force threw the eggs across the car. Now, I have heard of physics teachers who like to drill into their students, there is no such thing as centrifugal force. You're going to have a hard time convincing somebody with egg goo all over their car that there's no such thing as centrifugal force. Clearly something happened, but the problem, what somebody who says that is trying to get at in a maybe somewhat misguided way, in my opinion, but what they're trying to get at is that it's not really a force, okay? Calling it centrifugal force is misclassifying it. That's why I've put the word force in quotation marks. It's actually an inertia effect rather than a true force. A force is a push or a pull, and there has to be some object doing the pushing or pulling. So somebody explain it to me. What is, you know, like if I push a book across the table, that force came from me. Well, what does this centrifugal force come from? What object is exerting it? Well, there isn't anything. It's kind of a spooky, where did that come from kind of thing. It's actually the absence of a force that makes the eggs do that. So let's think about what this looks like from a bird's eye view here. To simplify the discussion, let's assume the back seat of your car is just frictionless. The more realistic thing is to say the friction is too small to hold the eggs back. But to make it a simpler discussion, we'll just say there isn't any friction at all. So if there's no friction, the eggs will obey the law of inertia. They will follow a straight line. Each of these little boxes here is supposed to be the car at different times. First the car is here, then the car is here, then the car is here. Notice the eggs inside the car following a straight line, like Newton's first law says they ought to do. The car around them is following the curve, which means first the eggs are at one end of the seat. Later on, the eggs are in the middle of the seat. And then in the end, there's the eggs reaching the other end of the seat. So it's the absence of a force that makes the eggs fail to follow the curve like the car around them does. That's what's really going on. But as I said earlier, the car is your frame of reference. And anytime you judge things from an accelerating frame of reference, you get these types of pseudo forces. If the car accelerates forward, it looks like there's a force throwing things to the back. If the car is accelerating toward the center of the curve, it looks like there's a force throwing things outward. And that's the nature of centrifugal force. Back over here to this little sketch I made a while ago. If you could suddenly turn off the Earth's gravity, notice, at the instant that the Earth's gravity got turned off, the moon would move away from us along a straight line. I remember I said that maybe 10, 15 minutes ago. Well, notice that a straight line would carry the moon farther and farther away from the center of its former orbit. So an object's inertia, its tendency to go straight, an object's inertia makes it want to move outward. And that's what centrifugal force is. So relative to an accelerating frame of reference, things appear to feel an outward force equal to mv squared over r. So 3 examples. The first one is another one of these conceptual things, like one of those little 5-point questions I might have at the end of an exam, or one of the little 2-point questions at the start of a quiz. So we have a fly riding around on somebody's ceiling fan, and it asks you for 3 things. Just draw arrows. What is the direction of the fly's velocity vector? What is the direction of the fly's acceleration vector? And what is the direction of the net force on the fly? Bugs can really hang on surprisingly well. Have you ever gotten in a car and there's like a bee or something sitting on the windshield, and you start driving away? You keep expecting the bug to blow off, and it's like, well, I'm up to 20 miles an hour. I'm up to 30 miles. Geez, I'm up to 40, somewhere around 30 miles an hour, maybe it finally comes off. But so you've got this fly clinging for dear life to the ceiling fan, getting very dizzy. And I'll pause it. You should pause it here. Okay, unpause. And the answers go like this. I'm not going to, for the sake of saving a little bit of time, I'm not going to draw all the blades of the ceiling fan. I'm just going to draw the one that the fly is on. So there's the center of it. And there's the blade, and that little dot there is the fly. An object's velocity vector points in its direction of motion. So velocity is that way. Next picture. This fly is in uniform circular motion. Ceiling fan just runs all day at the same speed. Doesn't speed up or slow down or anything. So in uniform circular motion, remember that's what the word uniform means in uniform circular motion, is you're keeping a constant speed. the fly is not speeding up or slowing down, so the acceleration does not have any, if the fly was speeding up, the acceleration would have a component toward the front. And if the fly was slowing down, the acceleration would have a component toward the back. But it's not doing either one of those things. It's just going around in a circle. The changing direction causes a centripetal acceleration. The word centripetal means toward the center. And it's the same thing with centripetal force. That centripetal acceleration is caused by a centripetal force. And once again, the word centripetal means toward the center. So that's the way you should have drawn the arrow for the net force acting on this insect. Next question, next two questions. Back. Sometimes I wish this thing just had frequently, I just wish this thing had a manual focus on it. Focus on the paper. Come on. Number 5. You've got a turntable for an old style record player. And I'm not sure what a dime is doing on it, but apparently there is a dime on the record player. So you turn the thing on, the record player rapidly picks up speed. And when the dime gets up to the speed that's given there, the thing flies off. What is the coefficient of friction? If you need some inspiration for this, use the question I did earlier about the car on the curve. That's that's actually quite similar. So I forgot to say pause. Hopefully you figured that out. If you didn't, there's still time, but you should unpause now and try that one. So just like in the one with the car on the curve, as the dime goes faster and faster, as the record player picks up speed after you've turned it on, the friction force has to get bigger and bigger to match up with the higher and higher speed. The maximum speed corresponds to the maximum friction force. Just like in that other problem, the maximum friction force is equal to μs times n, and the normal force will equal the weight of the dime. So maximum friction equals coefficient of friction times the normal force, and the normal force is equal to the weight mg. Divide both sides by m. The mass drops out. So the answer would be the same if it was a quarter. Oh, V max. The other one asked for the maximum speed. This one asks for the coefficient of friction. So you're going to solve it for mu instead of for V. And then stick in the numbers. The dime slips when it reaches 0.77 meters per second. So right around there is the maximum speed. G is equal to 9.8. The radius of its path, it says the dime is located 10 centimeters from the center. Remember to convert that to meters. For these particular materials, it looks like the coefficient of friction is around 0.6. The next question. It needs to be a little higher. Somebody's driving around with some of those fuzzy dice hanging off the rear view mirror. So here we see them as the car is going around a curve. And gives you a hint. We're trying to find the angle theta, okay? This could be looked at as a problem that involves centrifugal force. As the car drives around the curve, the centrifugal force pulls the dice to one side, right? Or at least that's what it looks like from the reference frame of the car. So what's the angle that you'll have if you're driving at this particular speed and so on? Well, I kind of tried to give you some hints here. What you need to do is you've got the force of this. There's two forces on this thing. There's its weight pulling down, and then there's the string pulling at this angle theta from a vertical line. If you use sum of the forces in the x equals ma, where a would equal v squared over r, you can use that to get the x component of the string force. And if you sum of the forces in the y equals 0 to get the y component. Once you know the x and y components, then you can get some, you can get theta from some trigonometry, the arctangent of opposite over adjacent. So I almost think there was a problem like this in the review for the first exam, only that was a static situation instead of one where something was accelerating. But anyhow, I should stop talking and let you see if you can do this. And I'll erase the blackboard while you're working. Okay, unpause. F equals ma problem, start with the diagram showing the forces. Two forces act on the fuzzy dice: their weight and the tension in the string. I think it said 200 grams. Yep, 0.2 kilograms. So mg, mass times gravity, equals weight. 0.2 of a kilogram times 9.8. And you've got 1.96 newtons pulling straight down. I went with C for cord, or you could have, S for string, or T for tension, or F for force. I went with the letter C. Why not? X component of the chord, Y component of the chord. That angle theta there is our objective. That's the thing we want to know. Summation of the forces in the X direction is equal to MA. I mean, technically it's equal to M times AX, but AX is the only non-zero component that the acceleration has. The acceleration points right straight, you know, the acceleration's in a horizontal direction, so AX is equal to A. There is only one X force to put in here. That's this X component. So CX equals M times, since the car is in uniform circular motion for as long as it's on the curve, its acceleration equals V squared over R. Fill in numbers. 0.2 kilograms, 30 meters per second for V, and 250 meters is the radius of the curve that the car is following. So the X component of this force is points of, not meters, it's newtons, it's force. In the Y direction. Assuming the car is on a level, you know, it's on a horizontal road, it's not a helicopter or something like that. If it's just moving horizontally, then vertically the forces have to balance. All of the acceleration is in the X direction. There are two forces to put into this summation. So the Y component pulls up, the Y component of the chord, and the 1.96 pulling downward. Well, not too tough to solve that equation. The Y component so maybe for a little extra emphasis, I'll draw this triangle again, but we now know that you've got 1.96 on this side and 0.72 on that side, and the tangent of that angle would equal the opposite over the adjacent. All of this. Well, not that you really care about this number, but the tangent of the angle is about 0.3 something. So you take the inverse tangent of that. You go around this curve, your fuzzy dice will be leaning 20 degrees because, you know, as far as the real forces, rather than talking about pseudo forces, the centrifugal force, what's really going on is if the dice are going to follow a circular path instead of going straight, you have to have a force toward the center of the curve. So the string has to lean far enough to the side to make a big enough force toward the center. It has to provide the necessary centripetal force. And the proper amount of lean is just a little over 20 degrees. Top of the next page, it makes a good point, which is that you shouldn't always, some question asks, well, what's the tension in the string? And you shouldn't just assume that that'll just equal mv squared over r. The force toward the center of the circle has to equal mv squared over r. In this one that I just did, I should put the camera back there for a moment. The tension in the cord does not point toward the center of the circle. Tension in the cord points to some point above the center. The thing that points toward the center of the circular path is the x component of this force. So that's the thing that has to equal mv squared over r, not the string tension itself. So whatever is the net force toward the center equals mv squared over r. Okay, one more example, and then that's the end of section 5. And actually, this is a fairly simple example compared to some of the other stuff I've gone through. But the reason it's here is just to give me an excuse to talk about some related issues that I wanted to have an excuse to talk about. The question says, you've got something like the International Space Station, except this would be a higher orbit than the space station is actually in. But there's this astronaut inside, and the question gives the mass of the astronaut, 75 kilograms. Find the force of gravity on this person. Well, first of all, how about a couple of wrong answers? One wrong answer is to say, force of gravity, that's the astronaut's weight. Weight equals mg. So far, that's all correct. 75 times 9.8, oh, there's the problem. G is equal to 9.8 near the surface of the Earth. The higher you go, the weaker the gravity gets. We don't know G at this altitude, and so that prevents us from answering the question with weight equals mg. Maybe the more popular wrong way to look at this would be to kind of smile to yourself and go, tried to catch me, trick question. Everybody knows there's no gravity in space. The answer is 0. Yeah, that's not actually true. Gravity is what holds this thing in orbit. It's what holds the moon in orbit, which is a lot high. Most of the, most of the manned missions anyhow, the old space shuttle missions and now the International Space Station, that's actually just a few hundred miles above the Earth's surface. Earth's gravity is enough to hold the moon in orbit, and it's almost 250,000 miles up. So yeah, there's definitely gravity in space because, like I said earlier, if you could turn off Earth's gravity, anything orbiting around it would just leave along straight lines. So why then do the astronauts float around? Well, it's not because of a true, yes, they float around so you have apparent weightlessness in a vehicle like that. But that's actually nothing to do with being in space. You can do exactly the same thing quite close to the surface of the Earth. If I was riding in the elevator over here, and for some reason I was standing there holding this, dum-da-dum, here I am riding in the elevator, and all of a sudden the cable broke, and the elevator started to freely fall down the shaft. Actually, I think elevators are made in a way that's a little more complicated than that, so that the whole thing doesn't depend on just one cable, but as a hypothetical example. So I find myself in this little freely falling room. Now, the thing about free fall is that the gravitational acceleration is the same for everything. G equals 9.8 for this thing. G equals 9.8 for the room around me. So the ceiling doesn't catch up to the Sani hands, instant hand sanitizing wipes. And the sanitizing wipes don't catch up to the floor. If everything's going to accelerate at the same rate down the shaft, then this just stays right in the middle of the room and appears to float until we get to the bottom of the elevator shaft, and then you get a new physics teacher. But a significantly safer way to do the same thing is in an airplane. They've done this training astronauts for, since the early 1960s. All you have to do is get in an airplane, little airplane that looks a lot like a pencil here, and you get it going along kind of like that. And you don't exactly turn off the engines. You would just take them down to an idle, but you get it so they're producing no thrust, and you let the airplane freely fall for 20 or 30 seconds. Just like the elevator I was talking about, everybody inside the airplane, everybody and everything is going to just float around because the room around you is always moving at the same rate as you are, okay? You don't catch up to the floor, the ceiling doesn't catch up to you. Airplane gets to about here and the pilot says, I think I'd like to get some thrust out of those engines again, and he revs them back up and they get back over here again, and then they can cut the engines and do the same thing over again. And they'll do that 20 or 30 times on a training mission. YouTube is full of videos of this kind of thing. Just in the search box, just put the phrase vomit comet, which is what the astronauts named the airplane, because apparently in the early days of the space program, when they didn't have all the good drugs they have today, a lot of astronauts had some problems with motion sickness. But you'll find, you don't even have to be an astronaut these days. You can charter an airplane and get them to do that. It's got to be an airplane that's kind of designed for it. They take all the seats out of the cabin and put some padding on the walls and so forth, just to make sure nobody gets hurt when they start the engines up again. But a lot of people have done this. They've taken their video cameras along, and you can watch them from the safety of your own home. I've always figured I'd make a terrible astronaut. I don't even like roller coasters. So I don't think, besides, as the saying goes, Mars looks like a nice place to visit, but I wouldn't want to live there. Anyhow, if you look at these videos, people are just floating around at the same altitude that many of you have been yourselves in a commercial airliner. The difference is the commercial airliner was not freely falling, but if it was, that's what you would experience. So that's why astronauts float around. It's not because there's no gravity in space. It's not something to do with being outside the atmosphere. It's just simply they're in a freely falling vehicle. So I guess that leads to the other question of, okay, if all of these things that are orbiting around the Earth are in free fall, why don't they fall? As the phrase free fall would kind of suggest. And it works like this. This is the nature of orbital motion. Imagine you're playing baseball. That's the ground. And you're standing over here. and you've got the bat, and let's say you hit the ball dead horizontal, okay? And it starts heading along like that. Pitcher jumps out of the way. Well, of course, it doesn't continue to move horizontally for any significant time after it leaves the bat. I covered projectile motion several weeks ago, and as the ball moves horizontally, it also begins to fall faster and faster. So constant X component, accelerating Y component, and it follows a path. Got to pause for just a second. So you hit the ball horizontally, but after it comes off the bat, it starts to curve toward the ground and follows a path something like that. Hits the ground over here. Now, I've just oversimplified one little detail in this diagram, which is, as you've probably heard, the world is not flat. Over the size of a typical baseball field, the curvature of the Earth makes no difference. But if you imagine some way of shooting the ball really, really fast, don't quote me on this because I don't have it written down in front of me, but if I remember the figure correctly, it's about 17,700 miles per hour. So if you had some enormous cannon that could shoot the baseball at that speed, well, it would vaporize going through the Earth's atmosphere at that speed. But if you imagine a planet that's just like the Earth, except it has no air and has no hills or anything to get in the way, what would happen is, at such an enormous rate of speed, you know, if you hit the ball from, let's say, 4 feet off the ground, in the time it takes to fall 4 feet, the ball would have gotten several miles downrange. And that's far enough that the curvature of the Earth matters. So the picture actually looks like that. And the thing to notice is the ball isn't any closer to the ground than it was when you hit it. As time continues to pass, the ball will continue to fall, and the Earth's surface will continue to curve out from under it. And after about an hour and a half, you should duck, because getting hit in the back of the head by something going almost 18,000 miles an hour will hurt. Now, when I explain it that way, it sounds kind of silly, but really what they actually do when they launch a satellite is not significantly different from that. Well, the same basic principles involved anyhow. The rocket, first of all, gets the satellite up above the atmosphere, so you don't have to worry about air drag. And the rocket gives it the necessary speed, and then it runs out of fuel. Okay, you jettison the booster, and the actual satellite just coasts. It's not like they've got thrusters on them that are running all the time to hold them up. The satellite just is in free fall. Same thing with the moon. Actually, I find it a little on the scary side to think about this too much. If you sit there in the backyard and look up at the moon at night and say to yourself, you know, there's nothing holding that up. And it's really, really heavy. And, but it, you know, it just stays up there. And this is what it's doing. Because it's moving sideways at the same time that it falls, it just keeps missing the Earth, falling around it over and over and over again. So anyhow, that's the thing I wanted to explain as sort of background information for this question. So let's see, weightless astronauts actually in free fall. I said that. Yeah, I said all of that. Yeah, I distilled all that down to about 2 sentences on the note packet there. But as far as answering the actual question, we can get the force of gravity because that's what's providing the centripetal force on this astronaut. So gravity provides the centripetal force. Therefore, the force of gravity must equal mv squared over r. Astronaut's mass, 75 kilograms. Speed given in the question goes in for v. $8 million meters. That would be the radius to the center of the Earth, not the altitude above the surface. It up, 468 newtons. That looks like it's the end of section 5. Yep, I turned the page and it says section 6. So this is the end.